Good morning everyone. I am Tanushri Dalai from Civil Engineering branch, and today I am going to teach you your Theory 2 paper which name is Structural Design 2. So in the last class we basically discussed about the introduction part of the design of beams and what are the cross sections and its classifications. Then the design procedure of laterally supported beam, which have contained 9 numbers of steps. So we discussed about this in the last class, and today we will discuss about wave crippling and wave buckling, which is a major term in case of beam design. So first of all, due to the action of heavy concentrated load, that is the point loads, on a beam, a region of high compressive stress is formed directly under the loads. The upward reaction at the support also produces region of high compresses in wave. Such high compresses in the wave may lead to wave failure like wave buckling and wave crippling. The wave buckling is also known as vertical buckling, and the wave crippling is also known as wave crushing. So basically these two types of failure in the wave is due to for the same reason, that is load and reaction. We know that in case of steel structure we used basically I section as a beam. So while in a I section is consist of 2 numbers of flange and 1 number of wave. So while the load is acting on the top of the beam, so that is the surface of the flange part. So due to this load system, the failure in the wave portion is more as compared to the flange, because the cross-section area of the wave is very smaller than the cross-section area of the flange. So that's why this kind of failure will occur in case of wave part only instead of flange. Accordingly, when the beam is supported over 2 support, that is the columns part at the end of the 2 beams, so at this time the reaction will happen. So due to the reaction part, that is the upward reaction, there may be a chances of failure in the wave. So while due to the load the failure will be occur in the wave part, that type of failure is known as wave buckling, and due to the reaction, that is the upward loading system due to the supports of the beam, at that time the failure will be occur at the wave part, that is known as your crippling, also known as wave crossing. So wave buckling occur when the vertical compressive stress in the wave at the mid-height reaches the critical buckling stress, as the thin wave acts as a long slender column. It is generally found that rolled steel is likely to develop wave crippling before developing wave buckling. And wave crippling is in this case due to a concentrated load on the beam due to the reaction at the support. High compressive stresses are produced in the thin wave close to the upper flange or lower flange. As a consequence of this, the thin wave may develop a fold at a place close to the flange. That means whenever wave crippling is occur in a beam structure, then the failure is like a curve type section occur in the wave part which is nearer to the flange. That means at the top of the flange or lower part of the flange. And if the failure is wave buckling type, then the curvature section of the whole wave part will be occur. Okay. So you can see in this figure. So here you can see the first figure. It shows the wave crippling part. So you can see this is a curvature section which develop nearer to the flange section. Okay. So I know that whenever wave crippling is occur in case of beam, then it should be nearer to the flange. That may be lower part or that may be at the upper part of the flange. But in case of wave buckling, you can see the total depth of the wave is curve type of section here due to the loading system. And this is due to the reaction. Okay. So you can see this is the figure of a rail track where wave buckling is occur. You can see this curvature section shows the wave buckling section. And here the damp type section you can see this is a failure due to the wave crippling in case of I section. So you can see this is the flange part and this is also a flange part, and the middle portion, this one is the wave part, and the wave crippling is occur nearer to the flange at the top of the flange. So you can see and we can find out the wave buckling very prominently as compared to wave crippling. Okay. So this is all about wave crippling and wave buckling failure of the wave. So now comes to a numerical which due to the beam section. So here the question is design a simple supported beam of span 5 meter carrying a reinforced concrete floor capable of providing lateral restraint to the top compression flange. The UDL is made up of 20 kN per meter imposed load and 20 kN per meter dead load, assuming Fe410 grade steel. So this is your question. So here you can see what are the data givens. So first is span is given, that means the length of the beam is given which is 5 meter. Then the loading condition is given which is UDL type, and in the UDL two types of loading are there. First of all imposed load and second one is your dead load. Imposed load means the live load part which is 20 kN per meter, and dead load means 20 kN per meter. And steel grade is given as Fe410. So we can write L equal to 5 meter, then convert it into mm, that is 5 into 1000. Then live load is given as 20 kN per meter. Second one is your dead load which is 20 kN per meter. The grade of the steel is given as Fe410. The yield strength of the steel due to the Fe410 is 250 Newton per mm square. So this is all about your data givens of this question. So now we will calculate or design the beam as per the steps. So in case of step 1, we have to calculate the load calculation. So here, first of all, we have to convert all the loads into the factored loads. So we know that to convert the working load into factored load in case of steel, we have to multiply 1.5, which is a partial safety factor for the ductile material. So to convert the factor load of live load, we have to multiply 20 kilonewton per meter into 1.5. So which equal to 30 kilonewton per meter. Similarly, to convert the dead load into factored load, we have to multiply 1.5 into 20, which is equal to 30 kilonewton per meter. So now, the sum of the total factored load for the beam is equal to 30 plus 30, which is equal to 60 kilonewton per meter. So step 1 is finished. So now comes to step 2. So step 2 is all about the maximum bending moment and maximum shear force calculation. As we know that in this beam only UDL is provided, so that we have to only apply the maximum bending moment for the UDL part while a simply supported beam, and also the shear force for the UDL in case of simply supported beam. So we know that the maximum bending moment for the simply supported beam subjected to UDL is equal to WL square by 8. So we know about the W, which is the total sum of the bending moment formula is WL square by 8. So we know about the W, which is the sum of the total factored load which is coming on the beam, and L is given, so we can put the W value as 60 and L value is given as 5 meter. So 60 into 5 to the power 2 divided by 8, which is coming 187.5 kilonewton meter. Similarly, we know that the shear force value, that is the maximum shear force value in the simply supported beam while it is subjected to UDL, the value is WL by 2. So here we can put 60 into 5 divided by 2, which is equal to 150 kilonewton. So now step 2 is completed. So comes to the step 3. Here we have to find out the plastic section modulus required for the given beam. So by which we can find out the suitable section to design. So now we have the formula ZP required equal to M into gamma M0 divided by Fy. So here M stands for the maximum bending moment occur in the beam. So we know that we can calculate the maximum bending moment as 187.5. So we can put 187.5, and remember one thing, here the unit of the maximum bending moment is kilonewton meter. So while we put the value over here, we have to convert it into Newton mm. So to convert it into Newton mm, we have to multiply 10 to the power 6 in the 187.5 kilonewton meter. So now here we can put the value, and gamma M0 value is 1.1, Fy value is 250 for the Fe410 grade steel. So by calculating all these things, we have the value 825,000 mm3. So to convert it into centimeter cube, the value is coming as 825 centimeter cube. So this is all about step 3. We will discuss from the step 4 in the next class. Today this much. Thank you.